Let us now go to the first module, which is Introduction. Engineering thermodynamics originated as a subject in mechanical engineering with the start of the Industrial Revolution. So, basically Industrial Revolution heralded the era when things which until then were being done using manpower were beginning to be automated and being done with things like steam. It was realized that steam could actually be used to run machines, not only steam engines but many other machines, or it can be used to operate many things which until then had to be done with extensive manpower. Okay. So, basically this steam was generated by burning coal, and it could be used to run machinery to do many things. Okay. So, that heralded the Industrial Revolution. And since that time, actually engineers, especially mechanical engineers, are always looking at the efficiency of the device. Basically, the expectation is that I burn a certain amount of coal, or for instance, let us say I burn 1 kilogram of coal, I know the calorific value of the coal. Okay. So, what I expect to get as output work from the machinery is something which is close to this calorific value. So, if the calorific value of coal is, let us say 25 megajoules per kilogram, then I expect to get when I burn 1 kg of coal, I expect to get 25 megajoules of work from the device. That is under ideal circumstances. So, mechanical engineers would always measure the amount of work they were getting from the device and then compare it with the calorific value of the fuel and try to see where the energy is being lost. If it is not coming as output work, it must be lost somewhere. So, they always were trying to improve the efficiency of the devices that convert heat into useful work. Okay. So, basically we are burning coal and giving heat to as input to a device, and we are getting work from the device. So, that has always been the pursuit of engineering thermodynamics, particularly mechanical engineering thermodynamics. Okay. We give so much heat to the device, we get so much work from the device. What is the efficiency of the device? And how do we actually try to improve? So, these are the questions that mechanical engineers were asking, and they realized during these pursuits that certain things seem to be universal. Okay, and that you cannot really improve the performance of a device beyond a certain level, and they also realize that other things like if an engine operates in a cycle, the net heat that you are giving and the net work that you are getting always seem to be the same or equal to each other. So, they realize that certain laws, universal laws seem to be applicable, and of course, these were realized based on experiments, but now these laws are considered to be fundamental laws of the universe. Actually, they are stated without proof, but they are accepted to be fundamental laws of the universe. Okay. Now, Peter Atkins, a well-known chemistry professor who has written a lot of books on not only on physical chemistry, but also thermodynamics and so on, kind of nicely states sardonically laws of thermodynamics. Okay. So, first law basically says that heat can be converted into work, okay, as we just discussed. And he says the second law, according to him, the second law says, but completely only at absolute zero, meaning if you want to convert all of the heat into work, you need to be able to do it at absolute zero temperature. Okay. And the third law, according to him, which is universal, is that absolute zero is unattainable. Okay. So, basically he sums up the laws of thermodynamics in this manner: heat can be converted to work, but completely only at absolute zero, and absolute zero is unattainable. Okay. Most of you may also be familiar with Murphy's laws and reasons why things go wrong. There is a very uncanny resemblance between Murphy's laws and the laws of thermodynamics. For instance, one of the Murphy's laws that you may encounter is something like this: for something to become cleaner, something else must become dirtier. Okay. This you may consider as a colloquial form of the principle of increase of entropy. So, we actually reduce the entropy at some place by making it cleaner, but that comes with a certain price. So, when you clean something, you clean the particular object, but the surroundings become dirtier. Okay. So, when you sum up the increase in the level of cleanliness of the object and the increase in level of dirtiness of the surroundings and add them together, it turns out that overall the universe still becomes dirtier, and this does not balance out the other. At best, under the best of circumstances, this may balance the other, but under most circumstances, overall universe will become dirtier. Okay, that is the general observation that we see in real life, in nature. Okay. The second statement probably we are all familiar with: left to themselves, things tend to go from bad to worse. For instance, this is like our room that we occupy, our office space. On day one the office is spick and span, but as time goes along, the office becomes more and more cluttered, and it requires an enormous effort for us to put it back into the shape in which it was at when we actually occupied the office on day one. Okay. So, this is also something that we are familiar with in everyday life, and these sort of statements actually bear an uncanny resemblance to the principle of increase of entropy, which says that the entropy of the universe at best remains the same or always increases. Okay. So, there are many nice connections between Murphy's laws and the laws of thermodynamics. You can actually read the book and probably appreciate it even more. So, in engineering thermodynamics, as I mentioned, we are interested in the conversion of heat into useful work. So, that is the primary objective of engineering thermodynamics. Although this seems to suggest that we are looking only at direct engines, meaning only engines that produce work. Whatever ideas we develop are also applicable to reverse engines like refrigerators, which absorb or which take in work and do something useful for us. Okay. Now, in the context of converting heat to work, we will try to answer the following questions in this course. The first question, obvious question, is how much of the input heat is converted into work by the engine under consideration. So, this relates to the calorific value of the fuel and the amount of heat we are supplying. How much of it is actually converted to useful work by the engine? That is the first question that we will try to answer. The second question is, everything else remaining the same, what is the maximum possible work output? Okay. Understandable, this suggests that the amount of work that we are getting normally from the engine will not be equal to the amount of heat that we are giving it. So, that being the case, what is the maximum possible work output? It may seem that the maximum possible work output should be equal to the heat input that we are giving the engine, but quite interestingly, the laws of thermodynamics tell that that is not the case. In fact, the maximum is nowhere close to the amount of heat that we are putting in. Okay. So, this question is a very subtle question. At first sight, it may seem like the answer to this question is the heat that we are giving is the maximum possible work output. The law of thermodynamics states that that is not the case. Okay. The third question that we will try to answer is, what are the factors that affect the performance of the engine? In other words, it is putting out certain amount of work. I am also able to determine what the maximum should be. So, what I am trying to do is bridge the two. Why am I not getting the maximum possible? So, what are the factors that affect the performance of the engine and by how much? So, if we have a clear understanding of individual factors which are contributing to this difference, then we can address these factors one by one and try to improve the performance of the engine, so that we try to get as close to the maximum possible work output as possible. So, these are the three questions that we will try to answer, and we will develop a framework which helps us answer all these questions and try to get insights into the nature of these processes. Okay. So, the framework that we develop will not only be useful for analyzing direct engines, meaning engines that convert heat into useful work, but also engines that utilize work to produce a useful effect, like a refrigerator for instance, or a heat engine, or a heat pump, which are called reverse heat engines. So, these take in power and then they do something useful for us. So, a refrigerator, as I said before, keeps the refrigerator compartment at a low temperature, thereby preserving the food and other things that we keep there. Heat pump on the other hand, which is used widely in western countries, particularly colder countries, and this is used during winter time to pump heat from the outside ambient, which is at a low temperature, into a dwelling or a house and maintain it at a comfortable temperature. So, we actually pump the heat from the cold ambient into the house which is at a higher temperature and maintain it at that higher temperature. So, that is also a reverse heat engine which absorbs the work. As you know, normally heat will not flow from the outside ambient which is at a colder temperature to a house which is at a higher temperature. So, this has to be accomplished by supplying power or energy to a device. Okay. So, the framework that we develop is equally applicable to both, although we most of the times our discussions center on direct engines because they are probably little bit more intuitive to understand. Keep in mind that the framework is very general, applies both to direct and reverse heat engines. We will discuss the notion of macroscopic approach in the next lecture.